It has been nearly a century since astronomers first proposed the concept of dark matter to explain certain astronomical phenomena that could not be explained by visible matter alone. Dark matter is a hypothetical form of matter that does not interact with light or other forms of electromagnetic radiation. It is believed to make up approximately 85% of the matter in the universe, while visible matter makes up only about 15%. The presence of dark matter was first inferred by Swiss astronomer Fritz Zwicky in the 1930s. He noticed that the visible matter in galaxy clusters did not account for the gravitational forces needed to keep the clusters from flying apart. Since then, other astronomical observations have supported the idea of dark matter, including the rotation curves of galaxies, the gravitational lensing of light by massive objects, and the cosmic microwave background radiation. Over the years, dark matter has become a fundamental component of our understanding of the universe and lies at the heart of the most successful cosmology model, the LCDM model. The lambda cold dark matter, LCDM, model is the current standard model of cosmology, which describes the evolution and structure of the universe on a large scale. It is widely accepted by the scientific community due to its ability to explain a broad range of observations with high accuracy. The LCDM model assumes that the universe is homogeneous and isotropic on a large scale, which means that it looks the same in all directions and at all locations. It also assumes that the universe began with a hot, dense state known as the Big Bang, which is supported by evidence such as the cosmic microwave background radiation. The model includes two major components, dark matter and dark energy. Dark matter is a hypothetical form of matter that does not interact with light or other forms of electromagnetic radiation, but whose presence is inferred through its gravitational effects on visible matter. Dark energy, on the other hand, is a form of energy that permeates space and is responsible for the observed accelerating expansion of the universe. The LCDM model also includes baryonic matter, which is the ordinary matter that makes up stars, planets, and galaxies. Baryonic matter only makes up a small fraction of the total matter in the universe, with dark matter making up the majority. The model is further supported by various observations, including the cosmic microwave background radiation, the large-scale structure of the universe, the observed distribution of galaxies, and the gravitational lensing of light by massive objects. Gravitational lensing is a process in which the gravity of a large item causes light from smaller objects behind it to be bent and deformed. The gravity of a large object, like a galaxy or a black hole, bends and distorts the light from things behind it, a phenomenon known as gravitational lenses. This distortion produces a magnifying effect that enables us to view items that would be difficult or impossible to see without it. Despite its success in explaining many observed phenomena, the LCDM model is not without its limitations. For example, it does not provide a complete understanding of the nature of dark matter or dark energy, and there are still many unanswered questions about the early universe and the origin of cosmic structure. Furthermore, the hypothesis that dark matter is made up of particles that interact only weakly with other matter is difficult to verify because they are difficult to detect. Many experiments have been conducted to try to directly detect dark matter, but so far, none have been successful. The Standard Model of Particle Physics, which is the framework used to describe the behavior of subatomic particles, does not account for dark matter. This has led some researchers to propose alternative theories, including those that seek to modify our understanding of gravity itself. One such modified theory of gravity is called AQUAL, a quadratic Lagrangian. This theory was developed by Jacob Bekenstein and Mordechai Milgram in their 1984 paper, Does the Missing Mass Problem Signal the Breakdown of Newtonian Gravity? AQUAL is a theory of gravity based on modified Newtonian dynamics, MOND, who sought to explain galaxy rotation curves without needing dark matter. MOND is an example of a class of theories known as modified gravity and is an alternative to the hypothesis that the dynamics of galaxies are determined by massive, invisible dark matter halos. Since Milgram's original proposal, proponents of MOND have claimed to successfully predict a variety of galactic phenomena that they state are difficult to understand as consequences of dark matter. Galaxy rotation curves are the velocity profiles of stars and gas within a galaxy, and they have been one of the most compelling pieces of evidence for dark matter. According to the LCDM model, the velocity of stars and gas within a galaxy should decrease as the distance from the galactic center increases. However, observations have shown that the velocity remains constant, suggesting the presence of dark matter. The Aqual theory proposes that dark matter is not a fundamental particle but rather a manifestation of a modification to gravity. In this theory, gravity is asymmetric and becomes weaker at large distances. This modification leads to a similar effect on galaxy rotation curves as dark matter would have. The Aqual theory has been tested against observations of galaxy rotation curves and has shown to be a better fit than the LCDM model. These findings raise an important question: what if there is no dark matter? What if our understanding of gravity itself is flawed? While the Aqual theory provides a compelling alternative to dark matter, it is still a relatively new and untested idea. More research is needed to determine its validity and whether it can fully explain the observed phenomena. According to the astronomers Sanders and McGaugh, one problem with Aqual is its failure to predict the amount of gravitational lensing observed in rich clusters of galaxies. Regardless of whether dark matter or a modified theory of gravity is ultimately found to be correct, the pursuit of understanding the nature of the universe remains a fascinating and ongoing endeavor. The fact that we are still grappling with fundamental questions about the universe after nearly a century of research is a testament to the complexity and mystery of the cosmos. In conclusion, while dark matter has been a cornerstone of cosmology for nearly a century, researchers are still struggling to understand its true nature. The Aqual theory proposes a modified theory of gravity that can explain galaxy rotation curves without the need for dark matter. However, whether this theory or dark matter itself is ultimately found to be correct, the search for answers to fundamental questions about the universe will continue to be an ongoing pursuit for generations to come.